Can you hear me? Everybody, those on Zoom?
Yes, yes.
Okay, thank you. All right, so today we're going to have the last lecture in electrostatics. And so the next, so now on Wednesday, we are going to start with magnetostatics, all right? And the one thing that I wanted to do today, and then you will see it in some questions or homework for this week, I wanted to see, we've talked a lot about what happens when we have an unshielded charge. And we talked about the coaxial line, coaxial because the two cylinders have the same axis, right? And the axis of the cylinder is the one that goes through cylindrical structures along the z direction and then goes through the center of the cross section of the cylinder. So they have the same axis. They are called coaxial. They are used in many applications. And as a matter of fact, I wanted to show you, because last time I started talking about the use of these types of lines and why we have thicker cables, and in fact, you can ask yourselves what some of the lines that you're using are doing and why they are done this way. But I wanted to show you an example just so you can appreciate why we do these kinds of things, that they are not only, book examples, that they are practically made in real life, and they have, granted, more complex, but they have very important applications. So I will need to find these pictures. So bear with me for a moment, because I got some pictures yesterday as I was looking through my, so, okay. Let's see whether I put them here. So, okay. This one is something wanted. You have already seen those lines. They're HDMIs, all right? You're using them in your computers quite a bit. Have you ever wondered how they look inside? This is how they look inside, which is very interesting, all right? So it's a very complex structure, obviously, but look at what they are doing to bring together many types of signals. So at the center, I don't know whether you can see my, yes, right here, they have all of the optical fibers. They have them in a distance, obviously, so they don't quite touch each other. So they keep them in a distance with some kind of a low dielectric material. And then they shield them around. This is at the center. But then look at here, this one. This one is a coaxial line. The only difference is that it has multiple center conductors, because this way you send multiple signals. If you were to take away all of these conductors here, all right, to remove them for a moment, what you would have is exactly what we analyze. Now it's the next step, of course, not here, but there are design principles for these types of coaxials. The only thing that I wanted to tell you is that these coaxial lines are very much in use, and we use them every day. I talked about TV, but in reality, you use them whenever you have to to send video. All right, and nowadays, for example, what I'm doing right now is video. That cannot be sent without this cable here, which I'm holding. That's an HDMI. All right, this HDMI looks like this you have here in front of you. So all of these designs have been made possible because we started with the fundamentals, and eventually, the way it's done, it looks very complex. But if you think that all of them are shielded and grounded, the shields, all of these shields, the green, here, the green shield, the yellow, the blue, the pink, all of those are grounded. The moment they are grounded, they are totally isolated. Okay, and then you can design them independently. And then you just place them all together. The same thing with fibers. So people can make things smaller and more complex, obviously, by doing these kinds of designs. Multiple signals are coming through from camera optical signals, all right, for images, to video, to all kinds of other things, audio, the whole thing is coming through that. So Zoom is working because of these cables. And that's what we are, so what we are discussing, these coaxial lines, for example, as they call them, they're not just, theoretical. They are simple, so we understand them in a simple form to get a sense of how the fields, are excited, why the line operates like that, why do we have this kind of capacitance, and why shielding is important. But this is how they look, and I wanted to show it to you. Okay. Going back to this one, the other thing that I wanted you to appreciate is what happens if the shield is not perfect. What happens if your outer conductor, instead of being grounded, it's not? And we know what happens in terms of the electric field, all right? The electric field extends, we have seen that, extends to the outside. All right, which we are going to try to also remind you how to find, which you also had in a homework, if I'm not wrong. But the question is, okay, the field extends, but what does that do to the capacitance? That's my question. All right. So yeah, we have an inside field. You calculated that. Goes from the upper point here. Let me in fact write also, so you see better. So you have the field, all right, that it starts from this red conductor where all of the positive charges are, according to the way I excite it, all right? I put the positive pole of the battery connected to the inside the inner conductor. And then so the field starts there with the direction outwards, because always the fields have a direction from starting at the plus charge outwards, all right? You remember that. Okay, then the field arrives at the blue metal conductor here, and inside that conductor, the field is 0, here. All right, and then what happens to the outside, as you did in the homework yesterday? The field now is radiated by these positive charges like this. And the question that I have to you is, where does this field terminate? What do you think? Well, never if there is nothing around it. In the example that I gave you, let me put the example back. In this one, where would that, so let me also go here, okay? Let's assume now that your green conductor is not shielded. All right, so inside you're going to have the field. What is going to happen to the field outside if the green conductor is not shielded by accident, obviously, because the shielding, the connection, whatever you did, however they do those connections, it was not done well, maybe it broke, and so forth. So it's not shielded. How would the field, in this particular case, how would the field, if it were by itself, how would the field go? If it were by itself, the field would go like this. Do you agree? If it were by itself, without anything around it, the field will go like that, which is what we have in our example. Okay. Now, that's not, of course, by itself. So where would the field go? So obviously, that is not practical because there are other things around it. So where will the field terminate? That's my question. Let's think about that. Do you want to take a moment and think about it? I will just put the charges on the outer conductor. Assume that the only one that is not shielded is that one. So what do you think is going to happen here? Can I hear somebody who is going to offer some thoughts? Yes, it will, whatever, why is it going to go to the grounds, wherever there is a ground? Because the grounds are connected to an infinite sea of electrons that are available anytime they find a positive charge somewhere. So with these positive charges creeping up around the conductor because there is no shield, what is going to happen? Here, the negative electrons are going to come. They will see that, and of course, they are going to come near here. They will come as close as they can, forcing those charges to also come closer. All right, so instead of being uniformly distributed as they would be if they were by themselves, those charges here, that they were further apart, they will go closer here, and you will see all of these charges here. Okay, then we have the other conductor. Here also, there will be more negative charges here because they see the positive. So obviously, there are going to be other charges depending, all right, of which is closest. As a matter of fact, on the basis of just the observed geometry, I would say the most of the charges will be where I'm going to show them right now. Just on observing, there will be fewer charges here, and there will be more charges where the distance is smaller. Okay, they will crowd, coming closer, as close as they could, and then fewer charges in other places. Okay, in fact, here, there will be even fewer charges. Let's assume that that also was something like that. And there will be also negative charges here. So there will be positive charges coming there. So they will crowd in the closest locations. All right, so the field lines will go where? There will be field lines. They will go here, 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 here. Okay, and if, well, the other ones are further out, this is covering and so forth, we'll go to these ones like this. A little easier to show. All right, so what happens when the lines terminate somewhere? What do they create in circuit form right now? In circuits, all right, this is what happens in electrostatics. But now we are trying to move from 3D and electrostatics to something we can use in circuits, which is capacitance. All right, we've been bothering with electrostatics for 5 weeks because we want to talk about capacitance. So if I were to take the field lines out, what would I see from the circuit point of view? What people will show, if you talk to a circuit designer, they're not going to show you these electric field lines like that, which exist. They're going to come here and say, well, if you ask them what happens, they will tell you, this person will tell you that you have parasitic capacitances. You will have, that's what the person will tell you, one parasitic capacitance here, one parasitic capacitance here, one parasitic capacitance here, and one parasitic capacitance here. That's what they're going to say. That's how designers will do it. And what does that really mean if you have those parasitic capacitances? Let's now, all right, so because of one ground that was not materialized because of fabrication reasons, now we are facing the following issue. What is going to happen, therefore, if you have the field extended? We answered the first question. The field is going to terminate on other conductors in the vicinity, all right? And if there are multiple conductors, for every conductor they terminate to, there is going to be a parasitic capacitance. So there will be possibly many parasitic capacitances. So what happens? What do you do with these many parasitic capacitances? Let's deal with one only, all right? Let's assume that for us, for this particular geometry, let me add here. Okay, let's assume that we have, I'll take all of this and I'll copy it. Okay, now let's assume we have somewhere here a capacitor, a conductor. So I will erase all of this and I will assume that my conductor is here. This is obviously a very realistic possibility, all right, to consider that this is here. Let me assume that this is one here. Okay, so the field lines here, all of the electrons will go down there. The positive holes, excuse me, will go down there. So we'll erase all of this because the electrons that will show on the ground will be here. And the electron, as I said, the positive holes will be there because the electrons from the ground will be here, as close as they can to this coaxial. All right, so most of them will be around here. So the lines that you will see will look like this. All right, now there are two ways of calculating this problem. If I were to give you this problem and say, use approximate methods, use an approximate method to find this parasitic capacitance that shows here, and the equivalent of this capacitance will be like this. This is parasitic. Why do we call it parasitic? Because we never intended it in the design, all right? It came on its own. Everything that is not part of our design, but it's there, unwillingly it's included because of other issues that we have not taken into consideration. We call it parasitic, even if it can be very large, all right, as entity, but still is parasitic. It's like a parasite that is destroying our designs. So that's a parasitic capacitance C. If I were to say to you, you know what, use the easiest to you approximation to find this capacitance. You know what approximation means? It means to simplify something in this problem so you can calculate a parasitic capacitance more or less. We use a lot of approximations in design. So if I were to ask you to approximate something here so you can give me a capacitance, can I ask of you what kind of approximation, what kind of simplifications, if anything was possible, what kind of simplifications would you consider to be able to calculate this capacitance? Can I have everybody's attention? Check this out and tell me. What kind of simplification? Just tell me one, it's okay. I mean, you know, everything is possible.
Could you try just representing it as the plates, 2 plates?
Yes, one possibility is to say exactly, to say the following. Listen, I don't know how to do this, obviously. I don't have the tools, but I can do the following for you. I can take this area because this is the most important area in my design. And I can make the following simplification. I can assume, and I will do the purple, the simplification, so approximations here. I can assume that my blue conductor in that region is almost planar. So I will do here, let me see, this. I will assume that my blue conductor is almost planar in that region, all right? I will assume that more or less is in the same distance with where it is right now. Sorry, here. I will assume that is in the same distance. With the ground, I will assume that the ground is here. So here. Of course, there is air in between. There is nothing else. And I will make a guess. I will assume that if my fields here are very close to just this point, then I will make a guess that this one, this is my guess, all right, is going to be about, if this has a radius of A, I will assume that this is A at best, if not less than that. I will assume probably that is A over 2 or even smaller. You can make a 1/10 of A, it does not matter. Okay, so that's what it is. I mean, it does matter eventually, but it's an approximation from the time you set your approximations, all right? You are, from the time you articulate them, you're set. Okay, now, what is the capacitance for this case? I will also further assume that my ground is also this much. So what that means is that all of the charges are confined in this width, which is A over 2. All right? How much is the capacitance of this? Do you remember? The capacitance of this will be epsilon naught area of the upper conductor divided by H. Okay, and it, yes? Yes, see, that is usually people will tell you from experience. If it's a very large A, usually that's almost planar. So there will be, it has to be, the larger the radius, the more planar is going to be down there. And you can assume that the area is going to be about the radius. I did not make it like that because it's not that large of a cylinder. So I made it A over 2, but it's an approximation. The interesting thing here is that if you assume that this cylinder is a line, and usually lines, for example, when you design those lines that I show you, like an HDMI, they do not talk about the total capacitance, they talk about the capacitance per unit length. Because you never know, this HDMI, for my case, is much longer than yours. All right, so what's the point of saying I have an HDMI which is like 1 meter? Well, mine is not 1 meter, maybe it's like half. If there are cables, they never give a total capacitance, they give a capacitance per unit length. So you can translate it into whatever length you have, all right? So this capacitance here is gonna be per unit length, which means that if my area is the width here, width times length, assume that this was length, then practically, whenever I get C to be epsilon naught WL over H. I divide, and this is a total capacitance. I will divide this by L, and then I will have a capacitance, which is per unit length. And the capacitance per unit length will be C prime, usually you can show it. And it's gonna be epsilon naught W, which is A over 2. There is no L, divided by H. So what is the interesting thing about that? You know that your capacitance is linear, a linear function of the width you made an assumption. So, right, so now you have even, you know how this capacitance is gonna go. So if it's a linearly dependent on A over 2, and I assume that this is W, all right, this is, which is, I consider this to be W. This one is W. Then I have that C prime is epsilon naught divided by H times W, which means that this capacitance with respect to W is gonna be linear. So now I even have a design curve for my parasitic capacitance. This is the design curve for my parasitic capacitance. Very important, all right? Now, the interesting thing, there are two other interesting things that we need to keep in mind. Still on the capacitance. Let me move it to the lower here. Okay. In terms of H, how does the capacitance go? What is the dependence of the capacitance on H for a given W, obviously? Inversely related. So it goes as 1 over H, which means it goes like that. All right. Now, obviously, in all of these cases, as the one that I show you, these parasitic capacitances are created because there are other conductors around which are shielded. And obviously, these other conductors which are there for whatever reasons, all right, not as part of your cable design, of your line design, they're there. They're going to have a separation from your cable, which is much higher than, in fact, the radius of the cable itself. All right, they're going to be further, they're not there for a reason. If there is a designer and wants to put another line too close to it, it's going to design to be there. But if they are just there symptomatically because, you know, of other things that happen in your layout, these capacitances will be down here. The H is going to be high. The distance with the other grounds will be high. So your capacitance is going to be probably down here, if not in this range, which means all of your parasitic capacitances will be small. That is important to remember. So your parasitic capacitances will be very small. Why is that important to know? At the end, that's the only thing you need to know in trying to understand the impact of this parasitic capacitance. Why is that? Because if I look at my problem here, which is the coaxial line, all right, and let me make it thick. All right, if I look at this coaxial line, and this coaxial line has an inside conductor. All right. Then I have my capacitance per unit length, which I have designed it for this line. And my capacitance per unit length, if I have a dielectric in there, which is this, is given. I know from, it's like, remember how you found it from your homework? It's P epsilon naught, and then what? Do you remember? It has a logarithm in the denominator of b over h. So you have that. You have designed your circuit to be like this. So now what happens is that you have your capacitance per unit length. All right, so your capacitance per unit length here, I will show it as a schematic. Is that? This is a schematic representation of it. Yes. In the fiber optic. The total capacitance is super large, but you don't care when it comes to cables. You will see later in transmission lines, you don't care about the total, you care the capacitance per unit length. All right, keep that in mind, what I'm telling you, and I will just make a simple introduction to you have a very good question, but I need to see why it's only not the total, but the capacitance per unit length that worries us in transmission lines. Transmission lines, the ones that are long, all right? Okay, 1 second, I'll come to that. So here, for example, we have found that all of them here per unit length, all right, you have some kind of capacitance all around, and eventually the total of these, all of them are in parallel, all right, are all capacitances that are created. So totally you have a capacitance per unit length, which is in farads per unit length, say per meter, all right? And that is the capacitance for this infinite long line. Okay, now, because of parasitics, this is your ground, and because the line was not grounded very well and you have ground there, you're gonna have this also, parasitic capacitance. So in circuit form, since I put here, let me do it like that. In circuit form, since I have connected this one to a voltage source, like I did up here, all right, to V sub D. And unfortunately, the ground was here, was not on the outside conductor, as it was supposed to be. Then what kind of a circuit representation I'm gonna have? I'm gonna have C, the total C for the coaxial in series with the parasitic between VD and ground, all right? And let's assume now that the length is important so I don't confuse you. Let's assume that we do have a length here. It's not very long. In this particular case, instead of C, it's gonna be the total capacitance, all right? So this is per unit length. So the total capacitance will be times L, obviously there. And the total parasitic capacitance will also be times L, all right? Assuming that the conductor extends. What happens when you have two capacitances in series? Yeah, so the smallest one does what to your capacitance? It kills it, all right? A small capacitance, parasitic capacitance, in series with your own design capacitance, it eliminates it because the total here, capacitance per unit length, which unfortunately now becomes the capacitance per unit length for the line, all right, because the parasitic came unwarningly. So now you have the total here to be equal 1 over C, to be equal to 1 over C prime plus 1 over C, which implies the smallest, which is the C prime, is the biggest term. In fact, you can see it here. C total will be C prime times C, C plus C prime. C prime is very small, which means that the product of C prime, I mean, I can even take it one step further. And say here, since C prime is much smaller than C because it's parasitic, then my C total becomes C prime times C divided by C and becomes C prime. So what did an small error in the fabrication did for this particular cable? It reduced its capacitance to very, very small values. Why is that important? Your question. In lines, we will see something. Lines have both a capacitance and an inductance because of the length. And the capacitance and the inductance of the line define two things in the line. The speed by which all of the data are transitioning, all right? And that is called the group velocity. They define the group velocity. So when you send bits per second, that tells you how fast the bits will go. And in fact, in ideal lines, the group and phase velocity are about the same. So say the velocity of the line is going to be what? 1 over square root of, LC. All right. So it's gonna, if your C is different, if your C here is not the C that you have designed this for, but it's a much smaller C prime here, then your line is gonna change its speed. And of course, this cannot go over the, and the other thing is gonna change is what we call the characteristic impedance, which is also very important. And this one is L over C prime. So this L over C, eventually prime here. This is what is going to happen. It's going to change the group velocity of the line, and it's going to change also the characteristic impedance, which means that you have designed the line to send so many bits per second, and it's not going to happen. So your whole HDMI, so if I had this HDMI connected to my computer for a Zoom, I would not be able to have a connection. All right, this is how electrostatics connects to circuits, and this is how we make designs. So I wanted to show you this example so you can understand there are very practical implications of what we study, things that you have played with and you're using all day long. So every time you use an HDMI, you need to remember me and the coaxial line. I swear to God, if you remember that, you will never forget the coaxial lines. But this is exactly how things work, and that's why it's so important. Yes. L is length here. In this particular example. Yeah, L is length. Sometimes we call them coaxial waveguides. The waveguides is the old terminology for a line. We got rid of it. We use it only very specifically to make some differentiations between some types that there are different than transmission lines, all right? So we use line for us at this moment, yes. Yeah, it could be appreciative. Yes, it could be significant, but these entities that I showed you, V and Z naught, they have them L and C prime are in per unit length. All right, so practically V is gonna be, and then one is in H, Henry's, the other is F, farads. Henry's times farads gives a second square. So this is gonna give you meters per second, which is velocity units. Well, we'll see that. We'll see that after the midterm, after the break, when we go to transmission lines. But what I wanted to is connect electrostatics to circuits and eventually to what we're going to see next. All right, there is always a connection, and that's why grounds are so important. A lot of times people, I'm telling you, in all of my experience, when my graduate students go into the lab to make a measurement, they come and the measurements don't look anywhere where they are supposed to be. Most of the time, it's not their design, it's the grounding. They don't have a good ground in the experimental setup. So in any case, any questions about this? Now, what I would, yes. You go and check the ground. And usually there are two ways of doing grounds in our measurements, either through the connectors. So usually when we do probe measurements, we have these probes that come with two grounds and a middle they come down and they press. If the two grounds is like for balancing, all right? Because if you only have one ground, it's not a balanced line, so it has problems. But in any case, two grounds, one signal line. They come all and they press like this on your circuit. And this is the probe station. And when they press, if your probe is misaligned, if somebody has pushed it so hard in a previous experiment and then one ground looks like this, and then it does not contact well, then you lose your ground there. That's one problem. The other is when you do a hard connection. Hard connection, this is a contact connection. Hard connection is you go and solder it. You solder the ground, all right? And then the soldering is not very good. So it was either not done symmetrically, so you have only a teeny point of the solder connecting to the other. So there are a lot of things that you have to check. So that's what you go first. I mean, I tell every student, go and check the ground first before you start thinking that your design failed. And most of the time is that. So that is what I want you to do next. I have a quiz, which I did not give you, but it's very easy now that we have done all of this, and I would like you to try to do it here. So I will go from here to, I will assign it to you. I can do it from here. Okay, and I will assign it. It's called electrostatic field, but you see it's about capacitances. And I will assign it now. And I will also put it up. Let me see here. Did you see it? Did you see the quiz coming up? Yeah, it's gonna take you some time to go to Top Hat, like me. It's a Top Hat. And I will put so you can see the schematic easier. It's this one. Okay. What this has is the following. Pay attention to the following things. Look at the field lines. The positive Q is on the lower conductor. The lower conductor has the positive. The upper conductor has the negative. So the field lines go from the positive to negative. It's reversed from what we had in our designs, but it's the same capacitor, right? But pay attention, Q positive here, negative on top. And then it says the following. Now we have this capacitor and then we put a metal in there. Just a metal, floating, not really connected to any ground or anything. The metal is not connected to anything. So then it asks the following. It says, find which of the statement is correct. And it specifies, it gives you, for example, electric field in region 3 is 0. Electric field in region 3 is minus C naught, whatever, it goes down. So specify the right, remember that when this is not connected to anything, the positive charges will be down here, and therefore electrons from this metal are going to start moving. And every time electrons move in one direction, they will create positive charges. They will move the other direction, all right? As we have said. So look at that. Remember, this is not connected to ground or anything. Remember that. So if electrons move down, then positive charges will move up. So look at this, and then the rest should be easy to identify. Okay. Feel free to leave when you finish.